Something absolutely extraordinary is happening on our sun right now. And I need to tell you about it because the numbers are staggering. Over the past 5 days, a single region on the sun's surface has unleashed more explosive power than we typically see in an entire month. We're talking about Sunspot AR4366, a magnetic monster that has grown to nearly 15 times the width of Earth and shows absolutely no signs of stopping. What makes this even more remarkable is that scientists are watching this unfold in real time, and the data they're collecting is rewriting what we thought we knew about our star's behavior. Let me start by giving you the raw numbers because they're almost unbelievable. Between February 1st and today, February 5th, 2026, AR4366 has produced over 60 M-class solar flares and 6 X-class flares. That's not a typo. 6 X-class flares in less than a week. To put that in perspective, X-class flares are the most powerful explosions the sun can produce, and we're lucky if we see 1 or 2 in a typical month. But AR4366 fired off an X1.0, then an absolutely massive X8.1, followed by an X2.8, then an X1.6, and just 2 days ago, another X1.5. The X8.1 flare alone was the third strongest solar flare of the entire solar cycle 25, which began back in December 2019. We're talking about one of the top 20 most powerful solar eruptions recorded since scientists started systematically tracking them in 1996. What's fascinating about AR4366 isn't just the power of these eruptions, but the sheer relentlessness of the region. In a single 24-hour period between February 2nd and 3rd, this sunspot unleashed 17 separate solar flares. 17. The sun's surface in this region has been crackling almost continuously, like a massive celestial fireworks display that refuses to end. Space weather forecasters at NOAA have started calling it a solar flare factory, and that description couldn't be more accurate. The region contains 47 individual visible sunspots, spanning an area of 1,090 millionths of the solar hemisphere. That translates to roughly 124,300 miles across, or about 15 Earth diameters lined up side by side. Now, here's where the story gets even more interesting. When AR4366 first rotated into view on January 30th, it was relatively small and unremarkable. But over the course of just 5 days, it underwent explosive growth. Scientists watching the Solar Dynamics Observatory data saw the region expand at a rate that frankly surprised many of them. This kind of rapid development indicates incredibly unstable magnetic conditions beneath the sun's visible surface. The sunspot has what's called a beta-gamma-delta magnetic configuration, which is the most complex and unstable type possible. Imagine magnetic field lines twisted and tangled like a massive ball of yarn, with different polarities forced together in ways that shouldn't naturally occur. When these fields finally snap and reconnect, they release absolutely enormous amounts of energy in the form of solar flares. The immediate effects of these eruptions have already been felt across our planet. When that X8.1 flare erupted at 2337 UTC on February 1st, it triggered what's classified as an R3 level radio blackout, which is categorized as strong on the scale. The entire South Pacific region, including Eastern Australia and New Zealand, experienced complete shortwave radio communication failures for several hours. Aviation frequencies went dead. Maritime communications dropped offline. Ham radio operators found their signals completely absorbed by the suddenly ionized upper atmosphere. Emergency services had to switch to backup systems. For anyone who happened to be flying across the Pacific at that moment or trying to coordinate search and rescue operations, it was a stark reminder of just how dependent our modern world has become on stable space weather conditions. But the solar flares themselves are only part of the story. What really matters from an Earth impact perspective are the coronal mass ejections, or CMEs, that often accompany major flares. A CME is essentially a massive bubble of plasma and magnetic fields that gets hurled into space at speeds ranging from 1 to 3 million miles per hour. The X8.1 flare launched a significant CME, and according to NOAA's NLIL model simulations, that cloud of charged particles reached Earth's magnetic environment today, February 5th. The forecasters predicted it would deliver what's called a glancing blow, meaning the densest part of the CME would pass just north and east of our planet rather than hitting us head-on. Even this glancing impact has pushed geomagnetic activity to KP levels of 3 to 4, with the potential for an isolated G1 minor geomagnetic storm. What makes this situation particularly noteworthy is the timing and positioning. AR4366 is currently almost perfectly aligned with Earth. When it first appeared, it was on the eastern edge of the sun's visible disk. But as the sun rotates approximately once every 27 days from our perspective, this active region has been turning more and more toward us. As of today, it's positioned close to the center of the solar disk as we see it from Earth, which means any future eruptions will send their energy and material almost directly in our direction, rather than off into space away from us. Space weather forecasters are currently predicting a 75% chance of additional M-class flares and a 25% chance of more X-class eruptions over the next 48 hours. Those aren't small probabilities, and the region's magnetic complexity suggests these predictions are conservative, if anything. The comparison that keeps coming up in scientific discussions is to the famous Carrington Event of 1859. That historic geomagnetic storm, which remains the strongest ever recorded in human history, was caused by a sunspot that amateur astronomer Richard Carrington observed releasing what he described as a white light flare on September 1st, 1859. The resulting geomagnetic storm was so powerful, it caused telegraph systems worldwide to spark and catch fire, shocked operators who touched the equipment, and produced auroras visible as far south as the Caribbean. Current estimates suggest AR4366 is approximately half the size of the Carrington Event sunspot, which is simultaneously reassuring and concerning. It's reassuring because we're not quite at that historic scale, but concerning because we're far closer to it than anyone wants to be in our hyper-connected technological civilization. This is actually where the real story lies. The 1859 Carrington Event occurred when humanity's technological infrastructure consisted primarily of telegraph wires. Today, we have satellite constellations in low Earth orbit, GPS navigation systems that coordinate everything from agriculture to financial trading, power grids with interconnected transmission lines spanning thousands of miles, and communication networks that underpin literally every aspect of modern life. A Carrington-level event today would have consequences orders of magnitude more severe than what happened in 1859. Studies by the National Academy of Sciences have estimated that a severe geomagnetic storm could cause economic damage in the trillions of dollars, knock out power for extended periods across entire regions, damage irreplaceable high-voltage transformers that take months or years to manufacture and replace, force airlines to reroute flights away from polar regions due to radiation exposure, and potentially cause cascading failures across multiple interconnected systems simultaneously. The good news is that we're not there yet with AR4366, and we have monitoring systems that our Victorian-era ancestors could only dream of. NASA's Solar Dynamics Observatory provides continuous high-resolution imaging of the sun in multiple wavelengths. NOAA's Space Weather Prediction Center runs sophisticated computer models that can forecast CME arrivals with reasonable accuracy. We have warning systems in place that can alert power grid operators, satellite companies, and airlines when dangerous conditions are developing. But the existence of these systems doesn't eliminate the risk. It just gives us a fighting chance to prepare. What's particularly interesting about this current episode is what it tells us about solar cycle 25. Scientists originally predicted this cycle would be relatively moderate, perhaps even weaker than solar cycle 24, which preceded it. Those predictions have been consistently wrong. The sun has been far more active than the models suggested it would be, and we're currently past what should have been solar maximum, the peak of activity. Yet here we are with one of the most productive sunspot regions in years still cranking out major flares. Some solar physicists are starting to wonder if we might see an extended maximum period, or perhaps even a secondary peak, which would be unusual but not unprecedented in the historical record. For those of you interested in the positive side of space weather, tonight and tomorrow night offer excellent opportunities to see auroras at latitudes where they're not normally visible. The University of Alaska Fairbanks Aurora forecast shows the potential for displays overhead in places like Yellowknife, Edmonton, Winnipeg, and Thunder Bay. But more excitingly, auroras may be visible on the northern horizon from cities as far south as Seattle, Des Moines, Chicago, Cleveland, and Boston. The UK Met Office is forecasting increased aurora activity across Scotland and northern England as well. If you're in any of these regions, and the weather cooperates with clear skies, tonight between 10 p.m. and 2 a.m. local time is your best viewing window. Get away from city lights, look north, and be patient. The displays can be subtle at these lower latitudes, appearing as a faint green or reddish glow on the horizon rather than the dramatic overhead curtains you see in photographs from Alaska or Norway. The bottom line is this: AR4366 represents a significant space weather event that's still actively developing. It's not a civilization-ending threat, but it's a powerful reminder that we live on a planet orbiting an active star. That star is capable of producing events that have real consequences for our technology-dependent society. Over the next week, as this region continues its journey across the visible solar disk and potentially erupts with more flares, we're going to learn a tremendous amount about solar physics, space weather forecasting, and our own resilience in the face of these natural phenomena. The data being collected right now will inform our understanding for years to come, and for those of us who find space weather fascinating, this is exactly the kind of event that makes you appreciate both the power of nature and the ingenuity of the scientists who study it.